our chemistry minions, I have good news for you. Unit 9,
Last video.
last video.
We got to cover this last vocabulary term and concept in kinetics and equilibrium. It's entropy.
Entropy looks big, bad, and scary, but it's actually not.
Pretty simple.
Matter of fact, if you walk into your bedroom, you're going to understand probably a little bit about entropy right now.
After you understand what the word means, yeah. So, been saying this throughout the entire unit. Motivation for all chemical and physical reactions are to get to lower energy, so
Because
lower
it's
heat
more-
enthalpy, because it's more stable.
There you go.
And to get to create like more randomness and disorder,
Because that is,
favored by the laws of thermodynamics.
again, lower energy.
Right.
So
Because
lower energy is happy, stable.
nature doesn't put things together under normal circumstances. If I had a yard that I threw 1,000,000 bricks into, just like bricks,
Yeah.
and I let them be, I didn't touch nothing.
You
The
didn't put
universe
any energy into them.
didn't put any energy into it. The universe wouldn't stack them nice and neatly for me.
No.
It would leave them there. As a matter of fact, it probably over time would continue to spread them out, break them down, and make them
Correct.
more
Now,
randomly
now,
ordered.
now let's rewind a little bit to somebody that took the time to order those bricks all together. Nice big
Jeepers.
little thing. And then
Right.
what does the universe do to that
Pile
building?
of bricks over 1,000,000 years.
Eventually, it starts to fall apart,
Right.
dilapidate, and go down. We have to keep adding energy to keep it ordered.
Right, exactly. So the universe favors chaos, randomness, disorder, and because it favors chaos, randomness, disorder, that situation happens to be lower energy.
There you go.
So,
So again, this is going to deal with phases, right?
right.
So let's get into some phases.
Particle diagrams. So you got to draw at least 9 particles. We're going a little overboard. Solids, they got to touch, group them in the middle. Okay? Liquids, at least 9 particles. They've got to touch, but you want to touch both 3 of the 4 walls of the container. The bottom, the left, and the right. You can have more than 9 here just to kind of prove that it's a liquid. Aqueous. This one's interesting because we got to have a liquid phase. So you draw a little liquid in there, and then you draw, 9 particles spread out in that aqueous phase. You should not have them touching each other, but they should be in there under the water level. And then gas. We want to have at least 1 particle touching each wall of the container because that's what gases do. They fill up the containers, and they should not be touching each other either. There's not. So, that's our spectrum of phases. You could either have a solid, a liquid, an aqueous, which is either a solid or a gas dissolved in water, or you can have a gas.
Okay.
So let's order them.
Okay. So basically, the phase changes that become more random will increase in entropy.
Which is favorable.
Correct. So now look at that solid.
Very organized, not very random. They're packed in nice and tight, like a stack of bricks.
Structured. So that's the least random.
Right.
And then liquid,
Okay, so they're not as structured, but they're still touching each other. If I didn't know that touching 3 of the 4 walls meant that it was sloshing about and moving, I would say that this is a lot like a solid, but liquid, a little more random and disordered.
right. I like to think about it as if I'm a pure liquid, doesn't one molecule of that liquid know what its neighbors is, its identity?
It can move around.
But it's its same, right? Its neighboring molecule is always going to be exactly the same if I'm a pure liquid,
Sure.
right?
Yeah.
Every molecule of water in that liquid knows that its neighbor is water. There's no randomness there. Because then you move into aqueous, it makes a little bit more sense.
Oh, now, yeah.
Right? So now I'm a dissolved solute, I'm blue, right? But now my neighbor could be
A solvent.
a solvent
Or another solute.
or another solute. I add randomness there,
I understand where you're going now.
right? Because I'm still in the liquid phase, but now the randomness has increased because I really don't know who my neighbor is right now and who it's going to be in 5 minutes when MoNaCo shakes me up.
Yep.
Right?
Gas, as you can see, they're all spread out all over the place. They don't have any neighbors.
Completely random straight line motions in there, the
Ding,
definition,
ding, boom.
so they can go in any direction. So, as I go from solid to liquid, liquid to aqueous, or aqueous to gas, then that is when my entropy is increasing. If the phase doesn't change at all, then more moles is more random than less moles. That's basically the rules.
Yeah.
And then basically this practice just has to deal with, am I changing phase and which way am I going as far as randomness?
And am I producing more moles of gas or whatever? If I'm
Correct.
producing more, then you're definitely increasing chaos.
Right. So
I'll take the first 7, you'll take the next?
all right. Well, yeah, I don't even know if we need to do all 7, but we'll do a few. In the first one, I have a solid going to a solid and a gas.
So we got to see if there's an increase, decrease, or change in entropy. Chaos,
Entropy.
randomness.
Delta S.
So,
Well, I'm forming a gas. So isn't a gas more random than a solid?
and I take one thing,
One phase
and I'm producing other things.
right, 2 phases.
This
Isn't
is
that more random?
It's a decomposition,
Well, right,
which is by definition
more random.
random.
Right, but that doesn't match our previous stuff. But let's stick to the phases. All of a sudden now I got solid and I have gas, and gas is instantly more.
Yep. So you're going to look at
Random.
it from the phase point of view.
Yeah.
And I'll chime in with, some
Some
logic
other-
and reason.
So there are some other little indicators, but the phase is the key. Because here I got the same stuff. I got one water liquid on the left. I got one water solid on the right. Is solid more random or less random?
Decrease.
Decrease. It's less random. It is more structured. Okay.
Yep.
Okay. Here we go. So now I've got gas plus a gas goes to a gas. Okay. So now we can talk about synthesis if you want, but look at, I have 4 moles of gas on the reactant side, 2 moles of gas on the product side. I am becoming more ordered. So I decrease in my disorder.
And if you look at it from the logic, reason type of chemical reaction standpoint, you're taking 2 reactants and combining them to make one type of product.
Which is definitely more structured and less random.
It's a synthesis. You're making something, which means you're probably putting energy in to make it. So, less random and disordered.
There you go. Here, number 4, I have a solid becoming 2 aqueous things, so I have to increase. Aqueous is definitely more random than solid.
And if you want to look, it's a dissociation here. And dissociation means to break apart. And if you're breaking apart, then
More
you're becoming more random and disordered.
More random and disordered.
Logic and reason, amazing how it works.
Yes. All right, so number 5. Well, especially when you have the background. All right, so sometimes the logic and the reason takes, it comes with practice. Solid to a liquid. I'm going from very, very structured to less structured, so there my entropy itself is increasing. My disorder is going up.
Right. They were locked in place as a solid. Now they're rolling around freely past each other
Right.
as a liquid.
Now here we have carbon dioxide subliming, going directly from solid to gas. Gas is instantly more disordered, so I am increasing in delta S.
Now number 7, looks like we've got ions in the aqueous phase on the left.
Coming together to make a liquid.
Right, so that's a synthesis.
And I'm going from more random to less random.
And it's an association, not a disassociation.
Oh, there you
it's
go.
the opposite of a dissociation.
So
It's an
I have got to be
association.
decreasing in my randomness.
And you're going from aqueous to liquid.
Right there alone. Aqueous to liquid is my randomness is decreasing. Okay?
Carbon solid and oxygen gas making carbon dioxide gas. So I have a solid combining with a gas.
To make just gas.
Just gas. This
Ooh.
one.
This one is.
Solid super ordered.
Yep.
Gas super disordered.
But now I'm
Making a
But
gas.
I'm losing the order of the solid.
Right. So,
So
I
I'm
must
becoming
be.
more disordered.
Except that it's a synthesis too.
It is.
This one's got a star on it. I don't want to say no change because I don't
Yeah.
have all the data. But my inkling is to say this is an increase in disorder, but some might argue with me that it's not changing.
I can understand the argument, but just from a phase change perspective, the disorder is actually increasing because I'm losing the order of that solid. Yeah, so I think we're good with 9 through 15 as far
There's
as
really
us
not going to
leading
be any
into
no
it.
changes. We don't want to see no
Nope.
change in any of these answers. We
Nope.
want to see increase or decrease. We put the no change in there because, sometimes you could make the argument like I just did, but Mr. Milks is right. Go with the phase approach.
Yeah, the phase approach is really the key here. I want to see 9 through 15 done on your own. Take a stab at it, and then you can work on the practice too. But remember, it seems kind of counterintuitive that I'm increasing my disorder.
Right.
Right? Entropy is not the order of things, it's the disorder.
And if you really want to practice some entropy, thermodynamics, clean your room.
Yeah, see how long it stays clean.
One, you're going to put a ton of energy in
Yep.
endothermic reaction to order all the stuff you've got in your room.
Yep.
And then over the course of time, 3, 4, 5 weeks, whatever it is, entropy is going to take effect.
And things are going to get crazy.
I know it happens in my house.
Oh, yeah.
Bye, guys.
See ya. Woohoo! Woohoo!